The next application of the moving charge in the uniform magnetic field is the cyclotron. The cyclotron is a kind of particle accelerator. It means that cyclotron will accelerate the particle, the charged particle, to get the large kinetic energy. Okay. In many applications in physics, in medicine, or in engineering, sometimes we need particles that have the large kinetic energy, and we want this particle to hit the target and do something. Like if we want to analyze the target, the structure of the target, the strength of the target, or we want to know the how can the particle penetrate the target to see whether the target is okay, or it have some kind of hole or some kind of defect inside the target. Okay. And to accelerate the particle, we can do it in several ways. The cyclotron is one way to do that. The principle of the cyclotron is that if you have the ion charge here at the point P, okay, at this point, okay, you generate, you create the ion here at the point P, and then at this point is in between two D-shaped conductor. Inside is a hollow D-shaped conductor. We connect with the alternating voltage source. Okay, this alternating voltage source will create the electric field between the D-shaped conductor. Okay, the electric field here, and it means that the charged particle will be accelerated by this electric field and enter the D shape. These conductors are placed. These two conductors, two D-shaped conductors, are placed on the region with the uniform magnetic field. For example, it may place on the top of the pole, maybe north pole. In this case, it is a north pole because the magnetic field points upward like this, and the large permanent magnet. Okay. So we know that when the charged particle move in the magnetic field, it will follow the circular path. Okay, this dashed line is the trajectory or the path of the charged particle, and the radius of the charge, radius of the trajectory, R is the mv over qb, where m is the mass of the particle, v is the velocity, q is the charge, and b is the magnetic field. We also have that the angular frequency or the angular velocity of this particle when it's moved in the circular path is qb over m. Okay. The important point here is that omega does not depend on the radius r. It depends on the q, the charge of the ion. B is the magnetic field, and m is mass of the particle, mass of the ion. Okay. So when the particle move in a circular path in this region, the frequency of the circulation will be the same. I mean, it's a constant. It's not depend on the radius of the circular path, but the radius depends on the velocity of the particle. So it means that when the particle pass through this gap of this D shape, and these 2D shapes are connected to the voltage source, which means it produces the electric field here. It means that the particle will be accelerate between this gap, and the velocity of the particle will increase. Okay. When the velocity of the particle increase, the radius of the trajectory increase also. So we must have that the particle will orbit with a larger radius, larger and larger radius. Okay. And every time the particle passes through the gap, it will gain the energy from the electric field, and the velocity of the particle will increase, and the radius of the trajectory will increase. So the particle will move in a helical path like this. The radius of the trajectory will continue to increase until it reaches the maximum value of the system, which we denote here R. And then the particle will release, and then we will use this high energy particle to do whatever we want. Okay. We can calculate the velocity of the particle when it exits the cyclotron as V is equal to Q B R over M. Okay. We use this equation and we rearrange this equation to get V equal to Q B R over M. R is the maximum radius of the system. Okay. The important point here is that we use the alternating voltage source connect to this 2D conductor. Okay. We need the alternating current because we will switch the polarity of the conductor, of the D-shaped conductor here, with the same frequency of the circulation or the motion of the charged particle. Okay, so it means that, for example, if the charged particle is a positive charge, okay, at first we have the positive charge here and the electric field point in this direction. So the positive charge will be accelerated in this direction, and then it goes to the circular path due to the magnetic field here. And when the particle moves back to this point, the alternating source will switch the polarity, and which means that it switches the direction of the electric field. Okay, you can see that now the electric field will point in this direction, which means that the particle, the positive particle, when it comes to this point, it will be accelerate again through this gap, and the radius of its trajectory will increase. Okay. Again, when it comes back to this point, the polarity of the voltage source switch again. Okay, and the electric field will change the direction to this direction, and the positive charge will be accelerated again across the gap. So every time the charged particle move to the gap, it will be accelerated and gain more and more energy. Okay. We can do this by adjust the frequency of the alternating source to match with the angular frequency that due to the motion of the particle in the uniform magnetic field. Okay. To be precise, the frequency of the period of the oscillation of this voltage source will be the half of the period of the rotation of the charged particle in the magnetic field, because when the the charged particle move from this position to this position. This is the halfway of the full circle, right? So it means this time, the time the particle take to move from this position to this position is the half of the period of the full circulation. So it means that the period of the alternating source here must be the half of the period of the circulation of this particle. Okay. We know that the velocity of the charged particle when it exits the cyclotron is qBr/m. It means that we can calculate the kinetic energy. Okay, we can calculate the kinetic energy of the charged particle when it exits the cyclotron. The kinetic energy is half of mv squared, right? So it means that if we put v here, this v to this v, we will have that kinetic energy is half of q squared v squared r squared over m. So it means that we can adjust the kinetic energy by adjust the magnetic field or by change the radius of the D-shaped conductor. So we can have the particle that have the large kinetic energy as we want.